Let's take a look at a VB.NET implementation of a Quicksort. I've actually written 3 different versions of a function which will partition a list. Let's take a look at what we've got. This is actually the first button code. All I'm doing here is declaring an array variable and populating it with some random data. So this is the list I'm going to sort. This loop here is simply building an output string which is the original list before it's sorted. You can see here I'm calling the partition function. I'm passing it the array and I'm passing it the lower bound and the upper bound of the array. And then this loop builds another output string which is the sorted data. Here's my first version of a partition function. As you can see, I'm passing in the array by reference, so that the calling program can get a hold of the data once it's been sorted. I'm taking the leftmost value of that array and I'm assigning it to be the pivot. I'm also setting up a variable called current pointer and I'm initializing that with the word right, so my current pointer will be the right pointer to begin with. The main loop here will run while the left pointer is different from the right pointer. And then, very much like the algorithm I previously described, we set the current pointer to be the right pointer, we compare the value at the right pointer with the pivot, and if necessary we take the value at the right pointer and move it to the position given by the left pointer. Then the left pointer advances, but we also make the current pointer the left pointer, so the left pointer will continue to advance. If there's no need to move the data like this, then the right pointer simply advances. Notice how we're decrementing the right pointer because we want it to advance towards the left pointer. Pretty much the same thing happens here if the current pointer is the left pointer. Once we've exited the main loop, we can then take the pivot value and assign it to the position given by the left pointer, or the right pointer, it doesn't matter, they're both the same. Notice I'm also returning the position of the left pointer as well. That's particularly important if we're going to use this partition function in a recursive quicksort program. So let's give that a whirl. There's my original list. The value 5 is the leftmost value. And here's my partitioned list. You can see that 5 is now in the correct position. Everything to the left of it is smaller than 5 and everything to the right is bigger than 5. Here's another version of the same function. I've called it partition 2. As before, we're passing in the array by reference. We're taking the leftmost value of the array and assigning it to be the pivot. And then we've got a main loop which will run while the pointers are different, but I'm doing it slightly different now. Notice that this loop is advancing the right pointer while the data at the right pointer is greater than the pivot, and of course the left and right pointer are not the same. This loop continues to run while there's no data to be moved. Once we've dropped out of the loop, we can then take the data at the right pointer and assign it to the position given by the left pointer. At this stage, the left pointer begins to advance, and this loop continues while there's nothing to be moved. When we drop out of the loop, we take the data from the left pointer and put it in the position given by the right pointer. A rather elegant way of achieving the same effect. Once we get out of the loop, we take the data at the pivot and assign it to the position given by the left or the right pointer, and as before, we return the position of the left pointer, which of course is the position of the pivot. Let's try this one. Exactly the same result. The 5 has found itself in the right position. Here's my third version of the partition function. This version doesn't explicitly nominate a pivot value, but it's similar to the previous one in that we have a loop which will run while the pointers are different, And inside this loop we have a loop which advances the left pointer until such time as it's necessary to swap the data at the left pointer with the data at the right pointer. And that's exactly what's going on here. We're using a temporary variable to do that. If a swap has taken place, we begin to advance the other pointer, and that will continue to advance until such time as a swap is necessary. And again, that's what's going on here. When the main loop finishes, we can return the position of the pivot value, which is either the position of the left or the right pointer. It doesn't matter which. Let's see what happens when we run this one. A different result from the previous two versions. Notice this time then that it's the 8 which has found itself in the correct position. Inadvertently, it was the value on the right hand side of the list which acted as a pivot. So we now have a sublist to the left of the 8 where all the values are smaller than 8, and a sublist to the right where all the values are bigger than 8. Any one of these three methods can be used to do a quicksort. So let's see how we do a quicksort. This is my final button code here. Notice I'm calling quicksort this time, I'm not calling the partition function. Quicksort has been written as a procedure, but notice that it still takes the array and the lower bound and the upper bound of that array as parameters. Here's the quicksort procedure. This is just like the algorithm I described in a previous video. While left is less than right, in other words, we have a sublist to process, we call the partition function. We pass the partition function the same parameters that we saw before, the data itself, a left and a right, and the partition function returns the position of the pivot value. The position of the pivot value effectively defines the top of the left-hand side sublist and the bottom of the right-hand side sublist. And then we've got our recursive calls. And as I said in my previous video, the quicksort function focuses on the left-hand side sublists while it can. Then it turns its attention to the right-hand side sublists. So let's see this one in action. A sorted list. Now a nice way to see what's really going on here is to step through this code. I'm going to set some breakpoints on the quicksort procedure definition, on my call to the partition function, and when quicksort calls itself. I'll run that up, and now I'm going to open up a watch window so I can see what's going on. In this window, I want to watch the data array to see it changing. And I also want to see the values of the left and right pointers. And finally, I'd like to see the value of the pivot position. So let's press continue. I can see in my watch window, there's my original array. I can also see we passed in a value of 0 for the left pointer and a value of 7 for the right pointer. Pivot position is currently 0. If I hit continue, the partition function has now done its job. I can see the 5 is in the right place, and I can see I have a pivot position of 3. Quicksort is now going to call itself with a left pointer of 0 and a right pointer of 3 minus 1, which is 2. Let's continue again. And notice my right pointer value is now 2. That means this invocation of quicksort is only looking at this sublist here. Another nice thing to see is the call stack. I'm going to switch that on. So here's my current call stack. That's the form code. There's my first invocation of quicksort, and here's the current invocation of quicksort at the top of the call stack. I'm going to press continue repeatedly, and I can see the call stack growing and shrinking, and I can see the values of left and right pointers changing. Notice the right pointer is now -1, so we're going to have an invocation which comes to a very sudden end. This is something you can do yourself. It will definitely help you get close to the way it works. Eventually, the call stack is torn down, and there's my sorted list.